Good afternoon, everyone. Today I am going to give my lecture topic on lithography in VLSI technology. Myself, Dr. Taslima Ahmed, Associate Professor, Department of Electronics and Communication Engineering. The content of my talk is firstly introduction, then IC fabrication, after that methods of photolithography, different types of lithography techniques, electron beam lithography, and then conclusion. Firstly, introduction. As we know that IC technology is divided into different types. The first one is small scale integration, large scale integration, then very large scale integration, ultra scale integration, and giga scale integration. Here, the main part of study is very large scale integration. That integration parts are divided accordingly according to number of transistors on a single silicon wafer. Very large scale integration contains number of transistors more than 10,000. Very large scale integration is the technique for fabrication of an integrated circuit by combining thousands of transistors into a single silicon wafer. VLSI integration that is begun in 1970s when complex semiconductor and communication technologies were being developed. The oscillator is the first VLSI device. Before the introduction of VLSI technology, most ICs had a limited set of functions they could perform. Due to small size, the weight of IC also reduced. There are different centers for fabrication of an integrated circuit. Here in India, we can see the different centers for fabrication. First one is wafer fabrication facility at ECIL Hyderabad. Second one, discrete components and low-end ICs are manufactured at BAIL, Bangalore and CDIL, New Delhi. Third one is high-end ICs are designed at Microelectronics Greater Noida, Cadence Greater Noida, ITI Bangalore, Semiconductor Complex Limited, Chandigarh. Fourth one is Sripilani also has largest design center. This is exclusively dedicated to R&D in the field of semiconductor and ICs for design and fabrication. Old IITs, mainly Kanpur, Delhi, Mumbai, Chennai, Kharagpur, Bangalore, are also have design facilities. Development of different IC technology that is shown by this tabular form as the inventor and the year of invention and the circuit. The first IC silicon was developed in 1958 by Jack Kilby Fairchild Semiconductor Center, and the first MOSFET was developed in 1960 at Kang Bell Lab. Then the first commercial IC was developed in 1961 at Fairchild Semiconductor, and then the first CMOS was developed in 1963 by Frank Witness at Fairchild Semiconductor, and then silicon gate IC technologies was developed in 1968 by Federico at Fairchild Semiconductor, and recently the capsule for endoscopy was developed, and that is the development at Jarklin Semiconductor. The basic steps for fabrication of an integrated circuit are shown in this diagram. As we know that the raw materials used for semiconductor material, that is silicon dioxide, react with carbon, and then we can fabricate our single silicon crystal. And after the development of single silicon crystal remove the different seed and other end of the ingot. The cylindrical structure that is obtained is mainly known as silicon ingot, and the grinding to special diameter and then ground some flat region. After that, we have to slice our ingot by using a diamond saw. After that, the wafer lapping and edge grinding is applied by using aluminum oxide and glycerin. After that, etching process is used for removing of surface damage, and then apply the polishing technique for mirror-like finishing of the surface. And then cleaning, for cleaning purpose, we are using wet and dry cleaning according to applications. Different types of hydrochloric acid, then sodium hydroxide are used for cleaning purpose. And then inspection, and last one is packaging. And then the lithography steps can be explained with this diagram clearly. Why require lithography and how lithography is applied? Because lithography process is applied mainly for selection of doping area over the silicon surface. As we know that MOSFET and digital structure, there are different doping areas. We firstly fabricate our silicon wafer by using simple technologies. For that, we have to use metallurgical grade silicon, and metallurgical grade silicon is converted into electronic grade silicon by using purification process. And after electronic grade silicon, we are obtaining single crystal by using CZ process. And after CZ process, we have to use different cleaning, polishing techniques to finally obtain the wafer. And that wafer is P type or N type according to doping material during the CZ process. And after preparation of that wafer, we have to apply doping of P-type material on the N-type wafer and N-type doping over the P-type wafer. And for that, we have to use firstly the oxidation process. As we know that MOSFET contains one oxide layer that is known as silicon dioxide, and that silicon dioxide layer is grown by the technique of oxidation, and that was introduced by Deal and Grove. And after that, we have to apply one photoresist material over the silicon oxide layer. And we also have to use the mark in a particular alignment angle so that we can expose the light into a particular portion of silicon wafer. And after application of light or X-ray or E-beam, we have to etching our surface for the removal of further silicon dioxide. And during the process, the removal process is also done by using different types of acids. And after that process, we have to apply our doping material or diffusion process across the selected area. Here, the types of lithography, and that is dependent on the types of lithography technique we are using and the input we are using here for lithography. First one is X-ray lithography by using X-ray. Then second one is electron beam lithography by using electron beam. And then photolithography, mostly used technique, that is by using light. The photolithography technique. What is photolithography technique? That is explaining here the word photolithography. That means lithios meaning stone and graphia meaning write. Writing of different types of process or pattern, and that is our stone is known as photolithography where we are using light. It means quite literally writing on stone. In case of semiconductor lithography, our stones are silicon wafer, and our patterns are written with a digital sensitive polymer that is known as photoresist. Each pattern being printed on the wafer is aligned to the previously formed pattern, and slowly the conductors, insulators, and selectively doped regions are built for the final device. Then steps of photolithography. Here the simple process that explaining how this photolithography technique is developed. The general sequence of processing steps for a typical photolithography process is as follows. First point is substrate preparation. That is already we know that by using raw material, by using our silica and carbon, we are obtaining our substrate. And that substrate is also known as silicon wafer. As we know that silicon and germanium, both material are used for fabrication of an silicon substrate. But mostly used material is silicon because silicon has a larger band gap and silicon is easily available in environment, and silicon can be used for different types of fabrication process easily, and that's why that is named as silicon semiconductor material used for silicon wafer fabrication. After that, the photoresist spin coat technique. And third one is pre-bake, fourth one is exposure, and then post-exposure bake, and sixth one is development, and then post-bake. Here, firstly we show the structures because according to structures we have to apply our photolithography technique. As the MOSFET structure that is containing the substrate layer, and above the substrate layer there are two dope regions, and between these two dope regions there is an oxide layer for gate connection. Here there is source and drain that is used. We know that MOSFET has three terminals, and that are source, gate, and drain. And according to this structure, we have to apply our photolithography technique accordingly. As positive and negative photoresist mainly decide for fabrication for structure, as MOSFET or as for BZT. That's why the first three structures are shown before explaining the technique. Here, the N-type silicon substrate is used, and P-type dope region, and silicon dioxide layer that must be fabricated over the silicon wafer before doping process. And the BZT structure is containing three layers, that is emitter, base, and collector, and that is type of BZTR NPN and PNP. According to that, we can see that the lithography technique we have to apply for BZT structure is for three times, because after the substrate, we have to select the portion for P-type layer, and after the development of P-type layer, we have to select the portion for N-type layer development. And that selection process mainly obtained by lithography technique. Here the photolithography process is explaining by this simple diagram, and we can show that how the light is exposing to a particular area, and for that we have to use photo mark. Without this mark we cannot send our light ray, and for that we are using here UV light, and UV light is sending through the mask and across the photoresist that will be developed our particular portion for doping. And silicon dioxide layer is already present over the silicon wafer. Then that is diagrammatic representation of photolithography process. First one is preparation of wafer, that is already we know that, and then after that over the wafer we have to coat the photoresist material, and after coating we have to apply pre-bake technique, and after that we have to align the photo mask and then expose to our particular ray, and after exposing we have to use photo exposure bag, and after that we have to develop the particular portion, and after development we have to use etching and implantation technique, and last one is our strip resist. Now here see the diagram of photolithography, and that diagram mainly explaining how the photolithography technique is going on. And for that, the first part that is shown, the photoresist material is coated over the silicon substrate. And for that, we are using one rotating device, and that rotating device helping the photoresist material to be equally spread over the surface. And after that, we have to use the pre-bake. That means we have to place our wafer to a oven at a particular temperature, and after that we have to use our illumination of light, and we have to observe that process by the objective lens, so that the wafer and the mask are equally placed, and after that we have to use post-bake technique. That is also a technique where wafer is again placed to the oven for a particular formation of pattern, and then development. Here, the first part of photolithography is explaining. The first part is applying the photoresist by spinning technique. Here, firstly, a drop of light-sensitive liquid known as photoresist is applied to the center of oxidized silicon wafer, and then the wafer is accelerated rapidly to a rotational velocity in the range of 3000 to 7000 rpm for some 30 to 60 seconds, and then this action spreads the solution in a thin, nearly uniform coat and spins off the excess liquid. The thickness of the coat is obtained in the range of 5000 to 10,000 angstrom. Sometimes prior to the application of photoresist, the silicon wafers are given a backout at a temperature range, and then excess moisture from the surface can be removed for better placement of photoresist. The typically using photoresist is coated thin film photoresist. Then second part is pre-bake. The silicon wafers coated with a photoresist are now put into an oven at 80 degrees centigrade for about 30 to 60 minutes to drive off solvent in the photoresist, and it harden it into a semi-solid film. Then third one is already I'm explaining through the diagram also, and here we can see that is alignment and exposure. That is the main part of lithography technique, because depending on alignment angle, the area of selection for patterning is obtained. The coated wafer as above is now placed in an apparatus that is known as mask aligner in a very close proximity, about 25 to 125 micrometers to a photo mask. The relative positions of the wafer and the photomask are adjusted such that the photomask is correctly lined up with the reference line for obtaining the pattern on the wafer. Then fourth part is development. And development part is most important, because we are using negative photoresist and positive photoresist accordingly for the development of different structure of MOSFET and BJT. The polymerization process increases the length of organic sand molecules that make up the photoresist. This makes the resist tougher and make it essentially insoluble in the developer solution. The resisting photoresist pattern after the development process will therefore be a replication of photo mark pattern, and that gives us a particular area over the silicon substrate for fabrication. Here, from the diagram, we can clearly explaining the fabrication of MOSFET and BJT by using positive and negative photoresist. As here we see that by using positive photoresist, we can apply our middle portion of the area for selection for fabrication of diode, as light is exposed over the surface and that radiation are ultraviolet, electron beam, X-ray and ions, and the silicon dioxide is already developed over the silicon substrate. And over the silicon substrate, we are using our photoresist material. And the photoresist materials are positive and negative according to application. And here we see that by using positive photoresist, the middle portion of the device is soft and that can be removed easily, and this technique is used for fabrication of BJT or diode. And by using negative photoresist, here we can see the middle portion is harder, and that particular technique can be used for fabrication of MOSFET, because in MOSFET we already seen there is a silicon dioxide layer in the middle of drain and source. And the fifth part is post-bake. After development and rising, the wafers are usually given a post-bake in an oven at a temperature of about 150 degrees centigrade for about 30 to 60 minutes to tougher further the remaining resist on the wafer. This is to make it adhere better to the wafer and to make it more resist to the hydrochloric acid solution used for etching the silicon surface. And then the second part type of lithography is electron beam. And in case of electron beam technique, this is a practice of scanning a focused beam of electrons to draw custom shapes on a surface covered with a electron sensitive film known as resist. The electron beam changes the solubility of resist, enabling selective removal of either the exposed or non-exposed region of the resist by immersing it into a solvent for development. The primary advantage of electron beam lithography is that it can draw custom patterns, that means direct writing. Here we are not using any type of mark, and here there is no alignment of this technique, and this helps us for direct writing technique, that eliminating the use of photo marks, and that is easily used technique for research and development purpose. The block diagram represents the electron beam exposure technique. Here again, positive electron beam resist and negative electron beam resist both are applied over the silicon substrate, and that is directly exposed over the silicon wafer. And after development, easily we can remove the silicon dioxide layer according to exposure area. And last one is conclusion of this process, that is lithography. Lithography is used to transfer a pattern from a photomark to the surface of the wafer. For example, the gate area of a MOS transistor is defined by a specific pattern. The pattern information is recorded on a layer of photoresist that is applied on the top of the wafer. Second one is the photoresist change its physical properties when exposed to light, UV ray, X-ray, and electron beam. The photoresist is either developed by wet or dry cleaning process, and That process can obtain by using exposure of light and that help us for developing a particular selection area for doping purpose. And from this study, I can conclude that how the lithography technique help us for selection of a particular area for doping over the silicon substrate and how the MOSFET and diodes are developed.